All right,
Ah,
welcome everybody. Yes, so our speaker today is Hao Chen from the University of Goettingen, and he will talk about gluing of minimal surfaces, recent progresses and future plans. Thank you very much for coming, and please go ahead.
Thank you very much. So this talk is about gluing constructions of minimal surfaces. The technique itself is not new, but I will report some recent progress. So this covers works that go back to 4 or 5 years ago. Some of these works are joined with Martin Traizet and Daniel Freese, and there are some ongoing works with other people. So in this particular text, by gluing, I mean actually desingularization. So I will start with a singular object and perturb it into a smooth object. And in this case, the smooth object is a minimal surface. So the first question is, what is a singular minimal surface here? So to explain that, I need to introduce the notion of noded Riemann surface. So there are two ways to see it. So first, you start with some punctured Riemann surfaces, and then you identify the punctures. So one puncture identified to the other, and they are identified into the so-called nodes. So the singular points after identification are called nodes. Or you can think of a noded Riemann surface as obtained from a regular Riemann surface by shrinking some cycles into nodes. So noded surfaces, they can be seen as on the boundary of the Teichmüller space. And later we will recall that to construct minimal surface, you will need some meromorphic forms on the Riemann surfaces. And as we shrink the cycles into nodes, so we obtain regular noded Riemann surface from regular ones, these meromorphic forms will have the limits that are called the regular forms. So how do we desingularize a noded Riemann surface into a normal Riemann surface? So this is done as follows. So consider two punctures that form a node. So here it's PI. So this picture is copied from a book. I forget which one. Anyway, so like here is a node. And you consider we remove a small disk. So here the disk around each puncture is removed. Then you identify the annuli around them with a relation that Z times W equals sigma. So here Z and W are their respective local coordinates around the punctures. And the sigma is a complex parameter. So when sigma equals 0, the punctures are simply identified. So these are the noded Riemann surface. And when sigma is different from 0, then the annuli are identified into a neck, as you see on the bottom right side. And so the conformal type of the resulting surface is determined by two things. One is the conformal type of the components, each component, so each punctured Riemann components before opening the nodes. And two is the parameter sigma. So we call sigma the node opening techniques. So there can be a different sigma for each node. So that's how nodes are opened. And then let me recall so we now have the Riemann surfaces. Now we can define Weierstrass parameterization on them. And so in this form of the Weierstrass parameterization that I show on the screen, we need 3 meromorphic forms defined on the manifold. And they need to satisfy 2 conditions. One is that, so here I need to explain that M is a Riemann surface, and these are some holomorphic forms, but actually if your minimal surface has ends, they can be meromorphic forms. So one condition that they need to satisfy is the conformal condition, and the other is called the period condition. So the period condition says that if you travel along a closed cycle on the Riemann surface, you should get back to the same point in the ambient space. So in my work, the ambient space can be the Euclidean space, three-dimensional Euclidean space, or a three-dimensional torus, flat torus, or the three-dimensional Euclidean space quotient out two parallels. So I don't know what that is called. Anyway, so and then the conformal condition ensures that this is a conformal immersion, and the parallel condition ensures that this surface is well defined. So I need to solve these two conditions. So the protocol of the gluing construction is this. So you first define Weierstrass data on noded Riemann surface, then you open the nodes, and at the same time, you extrapolate the Weierstrass data to the Riemann surface after the node opening. So this can be done because the meromorphic forms are actually defined by the parallels around the nodes. So after extrapolation, during the extrapolation, we will also solve the parallel condition and conformal condition by implicit function theorem. So from this procedure, we will usually come into two conclusions. So the first is that the conformal type of the noded Riemann surface must satisfy a condition that we always call balance condition. This usually comes from the fact that the parallel and conformal conditions need to be solved also at the noded limit. And the second conclusion is that in order to use the implicit function theorem, we need a certain non-degeneracy condition, which roughly says that any small perturbation of the conformal type will destroy the balance. So what happens if we don't have the non-degeneracy? Well, I don't know. I have seen many degenerate cases. Some are still limits of minimal surfaces, but some are not. So there can be all kinds of situations. So I just described the technique in a very general and abstract way. I hope it will be better after we see some concrete examples later. Here are some brief history. As I said, the technique is not new. The idea of desingularization traces back to very, very early, and application to minimal surfaces should trace it back to Capelleas, who also constructed many constant mean curvature surfaces by similar technique. But his method is based on PDEs, the analysis of PDEs, not on the complex analysis of Weierstrass data that I just described. So the one based on Weierstrass data is developed by Traizet. He glued saddle towers first by PDE method in 1996, then by a Weierstrass data method in 2001. Then he had a series of papers that glued catenoids into minimal surfaces. And these papers are more and more technical. And in 2005, he also worked with Weber to glue helicoids into minimal surfaces. So then what are the recent progress? Well, we glued catenoids again, and this is joined with Traizet. And I glued saddle towers again, and we also worked on helicoids, glued helicoids into minimal surfaces again. But wait, so these have been done by Traizet only. So what was left to be done? Do things get boring if we just work on this again and again? So actually not. There turns out to be more and more technical details to think about, and they become very, very interesting, especially the saddle tower part. This is technically the most interesting part, as you will see. So that's what I will try to explain in the following. So what was left to be done? So first, let's glue the catenoids. So here is what we would expect by gluing catenoids. So these surfaces, if you look from far, far away, they look like horizontal planes connected by very, very tiny catenoid necks. And when placed are infinitesimally close, the catenoids will degenerate to singular points, and the minimal surface becomes a noded surface. So more specifically, each plane is a Riemann sphere, and they are punctured. And each puncture so the punctures will be identified into nodes. And after you open the nodes, the punctures, open the nodes, they will become catenoids, very tiny catenoids. So we have mentioned that for the construction to work, the conformal type of noded surface must satisfy a balance condition. So in the context of luing catenoid, the balance condition only involves the positions of the punctures. And more specifically, the catenoid necks, they behave as electric charges in 2D space. And another description is that necks in the same layer, they attract each other, like electric charges of opposite sign. And necks in adjacent layers, they will repel each other, like electric charges of the same sign. And if they are further away, then they do not interact at all. So this is a very rough description of the interaction. So instead of giving you some mathematical formula, there should be no more than 5 in this talk. So I would like to point out that similar interaction can be seen in the morning when you have cereals in the milk, and they will attract each other actually. So they are like necks catenoid necks in the same layer. So actually this interaction is even quantitatively the same. So they are all logarithmic interaction, like electric charges in the 2D space. Anyway, so that was Traizet's work. So how did I get involved? So back in 2017, my wife and some other material scientists, they were observing structures of periodic minimal surfaces in experiment. So on the right-hand side is a photo from such an experiment. And after some analysis that I don't understand at all, they claim that this photo shows a structure of Schwarz D surface. Well, Schwarz D surface, we understand very well. A picture is shown on the left side. So, but there is more. They observed that there are actually 2 copies of Schwarz D surfaces, and they are related by a reflection symmetry in a vertical plane in the middle. So such a structure is called twinning in crystallography. And this is the first observation of non-trivial twinning in minimal surface. So my goal at the time is to prove rigorously that there can be twinning in minimal surfaces, in periodic minimal surfaces. So how can that be achieved? So first, periodic minimal surface can also be obtained by node opening, as I show in these 2 videos. Note that the nodes are arranged periodically. So if we cushion out the periods, each horizontal plane is actually a flat 2 torus with punctures. And punctures are identified into nodes, and nodes are again opened into small catenoids. And at the other end, you see Shirk towers and helicoids that we will talk about later. And here in the videos, you can see at the beginning, so let me do it again, how the node opening actually work in action. So they were very tiny, they open up, and the planes get away from each other, and so on. So, and in the video on the right-hand side, so at some point in this video, you are actually looking at Schwarz D surface. So Schwarz D surface is obtained by node opening in this way. So in the periodic case, the interaction, so I need to give another balance condition, must be described in terms of the vice class zeta function. So you don't need to understand this formula. So zeta is vice class zeta function. And the tau is, so 1 and tau is the spanning vectors of the torus. And then the xi is defined in this way in terms of vice class zeta function. And there is a constant on the right-hand side. So this balance condition works if we only open one node between each adjacent flat torus. And the balance, so this formula has another interpretation that if I have the constant on the right-hand side is 0, then the difference of positions of adjacent nodes, they correspond to the critical points. So this must be a critical point of the green function on the torus. So now let's consider the Schwarz D surface again. I said that they are obtained by opening nodes where the nodes are arranged in a triangular lattice. So nodes in each layer form a triangular lattice. And where is the node in the adjacent layer, in the next layer? Well, the green function on this particular torus has 2 minimum points. So here marked by A and B. So we can choose A, so keep choosing A. So we stack another layer of nodes at A and stack another at A, so keep going this way. And this will give you actually the Schwarz D surface, as you see on the left-hand side. So ignore the labels CBA, CBA here, because that's language from crystallographers. And here I would say that we are choosing, the difference of nodes are choosing to be this vector. So we are choosing A as the difference of position of nodes. So, but we can also make another choice. I first stack another layer of nodes at A, then for the second layer, I stack at B and A and B and back and forth. And this will give you this situation. So this is actually also a very famous minimal surface. It's Schwarz H surface. It has the helicoid hexagonal symmetry. So both are very classical examples known to Schwarz in the 19th century. So with this point of view, I would say that the twinning is obtained by stacking A, and suddenly you switch your choice to B and B, and go on. And then this would give you a twinning of Schwarz D surface. And this phenomena is very common in crystallography, and they are known as stacking fault. So, but mathematically, it is not obvious that we can do it because we now lose the vertical periods here. It means that if we have the period, we can just, for example, in here for the Schwarz D and H, we can simply open 2 nodes between 2 flat tori, and that's done. But if we have now no vertical periods, we then must open infinitely many nodes between infinitely many flat tori, and the stacking pattern is in general not periodic. So, but yeah, we need to open nodes between infinite many flat tori in a non-periodic way. So, but anyway, Traizet and me achieved this construction and confirmed rigorously that twinning can occur for periodic minimal surfaces, just as I described as stacking fault. So as I mentioned, this is achieved by opening only one node between each adjacent tori. So this simplification was motivated simply by convenience, because otherwise the balance condition would be too complicated to write down. But despite this simplification, we actually obtained a very rich collection of examples, surprisingly rich. within which the twinning is just a special case. So let me explain.
Can I ask you a quick question? So, isn't there still single periodicity left? Not that that helps, but you get some period in the twinning. Yeah, isn't there periodicity in the sort of
horizontal reductions?
Single periodicity sort of perpendicular to the screen?
Yeah, actually double periodicity. So
yeah.
Horizontally, there are still two parallels.
That's okay. That's also in the direction, I guess, left and right. I guess you have periodicity there.
Yeah, definitely
okay.
right and perpendicular to the.
Okay.
Yeah.
Okay. Thanks. Thank you.
Well, no, not necessarily left and right, because the parallels are not necessarily.
Yeah. Well, I just meant in the. You know what I meant? Yeah. In the plane, there's some doubly in the plane spanned by left and right and perpendicular to the screen, but not that lattice.
Yeah.
Got it.
Yeah. So anyway, so stacking forth is only a special case. Why? Because remember that for the triangular lattice, we have two minimum points. I marked A and B here. In fact, so these are minimum points. In fact, there are 5 critical points for the triangular torus. So we have 2 minimum points, and there are 3 saddle points at the middle of the triangular edges, triangular sides here. So so these are, how do you call it? So the order 2 points, if you use the group theory word. And in fact, a very deep result in 2010 claims that for any flat Q torus, the number of critical points is either 3 or 5. And that's a very fantastic result. And to give you an example of 3 critical points, that's the square lattice. So you have 1 minimum points in the middle and 2 saddle points in the middle of the edges. So these are the critical points of green functions on the torus. And I'm very surprised that this is only studied in 2010, only solved in 2010. And later, there have been other simpler proofs. And anyway, for us, this result from PDE theory becomes very handy, because for us, each of these 3 or 5 critical points corresponds to a position for the nodes in the next layer. So let's work on for example, for the triangular lattice. Each time I want to stack another layer of nodes, I have 5 choices. That's good. That's very nice. And any 5 choices actually will give me a minimal surface. So at each layer, so for example, I say the 5 positions in the triangular lattice is A, B, C, D, E. I can choose any bi-infinite sequence of these 5 letters, A, B, C, C, B, A, D, E, B, any one. And I place my nodes according to this bi-infinite sequence, and they all give rise to a minimal surface. What does that mean? That means that we can have uncountably many minimal surfaces. Each sequence will give me 1. And most of these minimal surfaces, they are not periodic, and even worse, they have no symmetry at all. They are not symmetric. And for physicists, they will be called disorders. So I really hope that they can one day see these minimal surfaces in experiment. Good, so that's just one result for the catenoids. Then let's move to the construction that glues saddle towers. Spoiler alert, this is technically the most interesting cases. So a saddle tower is something like this. Seen from far away, they look like vertical half planes sharing a vertical line in the middle. So these half planes, we sometimes call them wings. And in the middle, you have the saddle tower. So they are singly periodic with a single vertical parallels. Sometimes we always take the parallels to be 2 pi. And if we quotient out the parallels, a saddle tower is conformally equivalent to a Riemann sphere with punctures, and all the punctures are on the real axis. And these punctures correspond to, so each puncture corresponds to a Shirk end, a wing or Shirk wing. So that is, in general, yeah, the interesting thing is, in general, we actually do not know where the punctures are, but this is okay. So that's one amazing thing about the gluing construction. We don't need to know where the punctures are, and we can still construct. So I have mentioned that this construction is not new. This has been done before. So in this context, the saddle towers, each saddle tower is a punctured sphere, and punctures are identified to form vertical planes. So the nodes are these vertical planes. So you see that when I say glue something, it is not rigorous, because when I say glue catenoids, the catenoids correspond to the nodes. But when I say glue saddle towers, the saddle towers correspond to the punctured Riemann surfaces. But anyway, Traizet in 1996, he considered intersecting vertical planes and desingularized them by replacing each vertical intersection line by a saddle tower. So this was achieved first in 1996 by PDE method, then by complex analysis in 2001. So he made a lot of assumptions to make the construction work. One is that the surface must admit a horizontal reflection plane, and another that those three vertical planes intersect at the same line, and so on. And in 2009, his student Yunus, he glued saddle towers into periodic minimal surfaces. So he also assumed a horizontal reflection plane. So their idea is very simple. So the idea is, if you have a graph that is minimal, in the sense that it locally minimizes the length functional as like a 1D analog of minimal surface. So then this graph times R can be desingularized into a minimal surface. So this statement is not rigorous, but you don't lose much if you take this statement home. In fact, the minimality condition that the graph minimizes the length functional, this is equivalent to the balance condition. So, but I was not satisfied. I think something is missing, because in all previous constructions, we assumed a horizontal reflection plane. But for periodic minimal surfaces, if you count the parameters with the horizontal symmetry, we have only 3 free parameters. But it is known that the generic periodic minimal surface will have locally 5-dimensional deformation space. In fact, I recently constructed concrete examples of periodic minimal surfaces that have saddle tower limits. So these are actually deformation of the gyroid, but they do not admit any horizontal reflection plane. So my goal is to remove the assumption of horizontal reflection planes. So how can I achieve that? The idea is to use complex node opening parameters. So recall that the node opening is locally achieved by identify 2 annuli with the formula Z times W equals sigma. Z and W are local coordinates around the punctures. Sigma is the node opening parameter. And changing the complex argument of sigma will give you a then twist at the neck. And this twist corresponds to the phase difference between saddle towers. And with the symmetry, sigma is, so with the horizontal symmetry, sigma must be real. So the complex argument is either 0 or pi. The phase difference is either 0 or pi. So now we want to break the symmetry. So we need to allow complex arguments for sigma that have other values. And here is the new balance condition, a very subtle one. So after introducing a complex, so non-zero and a phase difference that is not 0 or pi, we can now state a balance condition that says the vertical force, as written here, at each point must sum up to 0. So this force has a term sine phi, where phi is the phase difference between adjacent vertices, adjacent saddle towers, and L is the edge length in the graph, and then you have epsilon, which is the nodal, so which is roughly how much you open up the nodes, and then you have a K, which is a real positive coefficient that depends. So it depends on the graph structure, but the dependence is very complicated, so I will not state it here. So this is the force each saddle tower is experiencing by adjacent saddle towers. So the balance condition says that each saddle tower must be balanced on, so meaning that the vertical forces along adjacent edges must sum up to 0. And with this new balance condition, we have many new examples. And for some reason, I'm most interested in periodic examples of genus 3. And here are all balanced configurations that could give rise to periodic minimal surfaces of genus 3. So there are labels on the directed edges, indicates that that's the phase difference of the ending saddle tower over the beginning saddle tower. So the first configuration actually gives a very famous surface obtained by Meeks in 1970s. And the second surface is a new one. This is another 5-parameter family of periodic minimal surface, and it's genus 3, and it contains the gyroid and also Schwarz edge surface. And for the other two configurations, we cannot conclude at the moment because they are degenerate. So we cannot use the implicit function theorem. But numerical evidence shows that they also give rise to minimal surface in the sense that they are limits of a sequence of minimal surfaces. Okay, and I said that saddle towers are technically very interesting. So here's one technical remark. Turns out that the horizontal forces vary in the order of cosine phi times the exponential something. So you see that the exponential part is a flat function. So it's very, very small when epsilon is small. So the variation of the forces is very, very tiny, but it should not be ignored. And here is a situation where this tiny variation makes a difference. So consider 2 saddle towers. So each has 4 wings, and you glue one pair of wings together. So there was a paper claiming that this configuration gives rise to an embedded minimal surface with parallel shirk ends. So, but this is actually not possible. By vertical balancing, we know that the phase difference here have to take the value 0 or pi. So the horizontal symmetry must be there. But because of the tiny variation of the force along this edge in the middle, the other shirk ends must bend to balance it. So they cannot stay parallel. So more specifically, if the phase difference in the middle edge here is 0, then the vertical shirk ends, these shirk ends, vertical ones, they must bend away from each other. Then the surface is indeed embedded. But if the phase difference in the middle edge is pi, the shirk ends will bend towards each other and they will intersect. And the resulting surface is not embedded. So that's a very interesting example. And then there are also many other interesting problems for the future. So in an ongoing project, we are trying to include this kind of vertices you see on the right-hand side in the graph. So such a vertex, they cannot be replaced by a saddle tower, but they must be replaced by a column of catenoids. And so for the first time, it means that we have to glue minimal surfaces of different nature. We are gluing saddle towers with catenoids. And such minimal surfaces do exist, at least numerically exist, as we see on the left-hand side. So we are working on this. And then I also dream to one day glue saddle towers with different speeds, different vertical parallels. So here I'm showing a video made by Matthias Weber. It suggests a continuous family obtained by sliding one saddle tower with respect to another. So I strongly believe that this is not possible, but I don't yet have a proof. So I have strong evidence, but I don't have a proof yet. So I think this video is misleading. So another interesting problem is, can we obtain, again, a defected or disordered minimal surface? So my idea is, so look at this surface. This is a periodic minimal surface where all the saddle towers have the same face. So they have the same face. All the same differences are zero. So can we flip the face of one saddle tower to pi? Or can we flip the face of just a few saddle towers? That would be in crystallography, they will call it a line defect. And if I can flip a lot of saddle towers, they will call it a disorder. And that's another interesting case for crystallographers. And let's be crazier. So can we desingularize this configuration? Some of you might recognize that this is the Bourne diagram. So they correspond to perovskite. So if this construction is successful, then we would have, for the first time, a minimal surface that deserves the name quasi-crystalline. So this is the first quasi-crystal given by minimal surfaces. So the difficulty of this task is that this thing has no parallels and no horizontal parallels. And the edge lengths in this graph, they can actually be arbitrarily small. So the nodes might interfere each other. So there are many technical concerns, but I dream to finish this. So finally, let me talk about our very recent work on gluing helicoids. And this is a joint work with Daniel Freese. So again, this construction was achieved before. So helicoids were glued into minimal surfaces that are invariant on the screw motions. And in 2005, Traizet and Weber did this, but they assumed that helicoids must lie along a straight line. And last year, Freese, who is a PhD student of Weber, he removed this assumption. He only assumed that the surfaces admit an orientation reversing symmetry, and it is possible that this symmetry is actually necessary. So we don't know yet. So our recent work, to be honest, is not a big progress in the construction technique, but it is about a very surprising interdisciplinary connection. So here you are looking at point vortices in two-dimensional inviscid and incompressible fluids. And our connection is that it turns out when we glue helicoids into minimal surfaces, the positions of the helicoids in the node limit, they must correspond to point vortices in two-dimensional fluids that are in relative equilibrium. So this means that the vortices, they move together as a rigid body. And more specifically, when the vortices are rotating as a rigid body, the same configuration of helicoids gives rise to a minimal surface invariant under screw motions. So this construction was achieved before. Then when the vortices are translating as a rigid body, then the same configuration of helicoids will give a minimal surface invariant under a non-vertical translation. And when the vortices are stationary and periodic, so you cannot work, this does not work for finitely many stationary vortices. So if they are periodic and stationary vortices, then the same configuration of helicoids will give you a minimal surface that are invariant under vertical translations. So under the translation 0, 0, 2 pi. So very unknowingly, if the vortex configuration is a finite one and stationary. The construction did not work because the parameter count just didn't give me any solution. So there is one period that is not close. So it's very annoying, and I don't understand why yet. It's just not beautiful. Another annoying thing is that all the examples that we constructed, they admit a orientation invariant symmetry. So is this symmetry necessary? That's our own big problem. So can we construct a, when we glue the helicoids together, is it possible to break the orientation invariant symmetry? So, but anyway, there are some annoying things, but we have a lot of examples. So this, now we have the connection. So what do? We can simply compare notes between minimal surface theory and fluid dynamics. So guess who would benefit more? Well, fluid dynamics, they have been studying vortex exterior since 150 years. And we only started glue minimal surfaces in 1996 or 2001, even the vice class data method is only in 2001. So minimal surface, we will benefit a lot. So for instance, the example obtained, so one example obtained by Traizet and Weber in 2005, they actually correspond to a vortex equilibrium known in 1885. So it means that if Traizet and Weber get to know some more physicists, they didn't need to write down half of the proofs in their paper. And then in 1988, Katia proved that you can actually twist a saddle tower into a, so the sharp ends will become helicoid ends. And this was in 1988, but the same thing, so in this case, the helicoids are arranged in a polygon, regular polygon. So this configuration of vortex is known to Thomson in 1882. Again, wow. And here are some experimental pictures taken from superfluids, where you can see vortices forming polygons. And the left-hand side is a minimal surface, and the right-hand side is the vortex configuration. And now some more classical examples. Riemann surface, Riemann minimal example. So not Riemann surface, Riemann minimal example. So we have two helicoids. They form a pair, and so I don't know which year is this, but no problem. They correspond to a pair of vortices rotating in opposite direction. And this vortex configuration, I think it traces back to the beginning of human society. And then Katia meets Rosenberg examples. So these are doubly periodic minimal surfaces, and they correspond to the very famous von Karman vortex street. And the von Karman vortex street is known in 1912, and the KMR example is constructed in 1988. So let's see. There are actually indeed some minimal surfaces that doesn't yet have corresponding, so the corresponding vortex configuration was not yet observed. For example, for periodic minimal surfaces, the corresponding vortex configuration would also be periodic. It is very difficult to do the experiments because it's difficult to get inviscid incompressible fluids. But anyway, I managed to find an experimental photo taken in the 1970s by Japanese automobile engineers. You see that these are a row of several parallel von Karman vortex streets. And the vortices are forming hexagonal lattices, but they will disappear very quick if you move rightwards. So this corresponds to the helicoid limit of Schwarz D surface. here the helicoids also form hexagonal lattice. Okay, and here is a new example. So on the right is a vortex equilibrium in action. So I promise that in making this video, I only fix the position of one vortex, because otherwise the vortex configuration will flow away together as a rigid body. But this is one of many vortex configurations known as the Adler-Moser configuration. So this configuration is actually degenerate. But if we, so degenerate means that I cannot use the implicit function theorem directly. But this is solved if we impose the symmetries in the real axis and the imaginary axis. So if we impose these symmetries, the configuration become non-degenerate, and we can use the implicit function theorem, and the corresponding minimal surface is shown on the left. And you can check that the helicoids are placed at the same positions as the vortices on the right. So that would be all for my talk. Thank you very much.
Thank you very much.